Okay, so now we're going to solve a system of linear equations. And then in part one, we're going to look at just basic concepts. And then in the part two and part three of this lesson, or these lessons, we're going to talk about how to solve them algebraically. But let's just discuss the basic concepts of a system of linear equations. So in the past, in previous courses, you learned that y equals 2x plus 1 is a linear equation. All right, and so a linear equation is an equation that can be written in the form ax plus by equals c. And remember, this is called standard form of a linear equation. All right, so ax plus by equals c. So you have, and this is in two variables. So you have your variables on the left and your constant on the right. So that would be standard form. Now this is not in standard form, but it is still a linear equation. If you notice, the exponents of both y and x are 1. So that's y to the first, x to the first. All right, but it's still a linear equation. You also recall that when you graphed this linear equation, the graph was a straight line. The graph was a line. All right, so the graph is a line. And hence in the word linear is the word line. All right, so when you graphed it, you ended up with the line. Okay, so that's one equation. You could have either graphed it using a t-table, or you graphed it using the idea of rise over run, the idea of slope, and the y-intercept. So you learned how to graph it both ways. Now, when you have this equation, let's say when you have two equations, two linear equations, and let's say the other one is y equals negative 3 halves x plus 8. So when you look at these two linear equations together, and normally we'll denote it with this brace that looks like this. So this would denote a system of linear equations. So a system. And so when you denote it together, this is called a system of two linear equations. All right, so a system of two linear equations. All right, and so the idea with these linear equations is that you want to solve these linear equations. You want to solve them. So we're going to discuss the idea of what does a solution of a linear equation mean? What does it look like? What does it mean? So we're going to graph each one individually first, and then the more efficient way, though, is not to graph, but the more efficient way would be to either use substitution or the addition method, which we'll discuss. But the basic concept, you can easily understand it, what it means if you were to graph it. So we're going to do the graphing part first. Okay, so basically we're going to graph y equals 2x plus 1. Now remember, there are a couple ways that you learn how to graph a linear equation in the previous course. One way is to use a t-table. So if I use a t-table, x and y, if I use a t-table, I would pick some value for x and then substitute into x and then solve for y. So for example, if x is negative 1, I would get y equals 2 times negative 1 plus 1. So 2 times negative 1, so x is negative 1 plus 1. And then 2 times negative 1 is a negative 2. Negative 2 plus 1 is a negative 1. So I get the ordered pair. Remember, I'm using the word ordered pair. I'm using the word ordered pair, so I'm getting the ordered pair negative 1, 1. And then you would plot that. So you would plot that point. So negative 1 here. All right, so that's this right here. Then I'd do another pair. So remember, in order to graph a line, you need at least 2 points. Now, remember, we're graphing these ordered pairs, so x and y, so alphabetical order. So we put them in alphabetical order. X first, y second. Now, if I were to let's say x be 3, I would get y equals 2 times x, remember x is 3, plus 1, so that's 6 plus 1, which is 7. So I get the ordered pair 3, 7. Now, you could have easily made a mistake with one of these calculations. So you may want to plot another point, 3 points, just to make sure that they all lie on the same line. And so if I, let's say, let x be negative 2, then I would get y equals 2 times negative 2 plus 1. So that's negative 4 plus 1, which is negative 3. Alright, so then I'm going to plot those points. So I'm going to plot these points here, these 3 ordered pairs on the coordinate plane, and I'm going to graph the line. So we have negative 1, 1, we have 3, 7, that's about here. We have negative 2, negative 3. So negative 2, negative 3 is here. Alright, so then I'm going to it's a good idea to use a straight edge to graph these lines. If you do it by hand, you could easily not draw it straight and not recognize what your solutions are. Okay, so one thing I need for you to also remember is that when you graph these lines, see all these things that are shaded, all these are solutions. Every point on that line is a solution to this equation we just graphed, y equals 2x plus 1. So that's what we just found. We found that when you graph a line, or when you really graph, let's say last semester when you graphed the quadratic functions, you were graphing solutions. So every point on that line is a solution to this equation. All right, now let's graph the other line. See, the other line was y equals negative 3 halves x plus 8. So let's graph y equals negative 3 halves x plus 8. Now remember what you did when you had a fraction. And let's go ahead and use the t-table here. So remember what you did when you had a fraction. You chose numbers for x to make things easy on yourself. You chose numbers for x. Now you could choose any number for x. You could choose any whole number, any integer, any decimal, whatever you want to, a fraction, any real number. But it is always efficient to choose a number for x that's divisible by this denominator. So my denominator is 2. So I'm going to pick numbers that are divisible by 2. If this was, let's say, 3/5, negative 3 divided by 5, I would choose numbers that are divisible by 5, and so on. So that way you don't have to deal with any fractions. So if you chose any other number that was not divisible by 2, you would have to deal with some fractions. You would have to add fractions together. Alright, so let's pick, let's say, 4, if x is 4. So if x is 4, I'm going to get y equals negative 3 halves times 4 plus 8. Negative 3 halves times 4 plus 8. And then you reduce. 2 into 2 is 1, 2 into 4 is 2. So I get negative 3 times 2 is a negative 6. And negative 6 plus 8 is a 2. So I get the point 4, 2. Alright, if I pick, let's say, x to be negative 2, I'm not going to have enough room in this, so let me, so I'm not going to, well, here's what happens when you pick negative 2. I get y equals negative 3 halves times a negative 2 plus 8. So this 2 and negative 2, they're both divisible by 2. So 2 to 2 is 1, 2 to negative 2 is negative 1. But here's what I get. I get negative 3 times a negative 1 is a positive 3. 3 plus 8 is 11. So I get the point negative 2, 11. The problem is that my grid doesn't go all the way. It only goes up to 9. So I really don't want to use this one. So let's try negative 1. Let's see what happens when I use negative 1. Oh, I can't use, see, I wouldn't use negative 1 either, because then you would have a fraction. So let's not use negative 1. So remember, you want to use numbers that are divisible by 2. Alright, so let's just keep with the positive ones and see what happens. So if x is, let's say, 2, I get y equals negative 3 halves times 2 plus 8. So the 2's reduce. 2 to 2 is 1, 2 to 2 is 1. So I get negative 3 times 1 is a negative 3. And negative 3 plus 8 is 5. Now let me just mention one thing before I go on. You could have chose any number. Remember, it doesn't have to be divisible by 2. But if you choose numbers that are not divisible by 2, you're gonna end up with fractions, and you're gonna have to estimate where those are on the grid. And when you graph them, if you're solving a system by graphing, it's not a very good idea to estimate. You want to make sure that you can pinpoint exactly where those points lie. So it's a good idea to pick points in which the point lies where the grids intersect when graphing. Alright, and then if you, let's say x be, let's say negative 6, let's choose negative 6, I get y equals negative 3 halves times a negative 6. I can't, let's not use negative 6 because that's going to be too big. Let's use positive 6. So negative 3 halves times a positive 6 plus 8. So let's see what we get. We get 2 into 2 is 1, 2 into 6 is 3, and negative 3 times 3 is a negative 9, and negative 9 plus 8 is a negative 1. So that's going to fit in that grid. Alright, so I chose numbers that will fit in this particular grid. Okay, so let's plot these. So I get 4, 2. So 4, 2 is here. I get 2, 5. Oops. Alright, so I get 2, 5, so I can plot 2, 5. So 2, 5's here. I get 6, negative 1. So 6, negative 1 is here. Alright, and so then I'm going to graph these. I'm going to graph this line. Hopefully it'll, the ruler's right on those points. So I'm going to graph these. Looks like this. So maybe it's a little off because it didn't go straight directly into it, but it'll be fine. Alright, so there's the graph of those two lines. So remember this line here, this one right here. Remember when you graph a line, you're graphing the solution. So every point on this line is a solution to this equation we just graphed. Y equals negative 3 halves x plus 8. So that's what we graphed. Okay, now here's the idea. So here's the idea. When solving a system of linear equations, to solve a system of linear equations, okay, you are looking for the point or points, there could be more than one, looking for the points that satisfies both equations. At the same time. Okay? So in solving a system of linear equations, you're looking for the point or points that satisfies both equations at the same time. So in terms of graphing, if you notice these two equations, do you see a point that is common to both equations? Do you see a point? Do you see a point that's on both lines at the same time? So for example, this point here, is this point here on the other line? The answer is no, it's just on this line. Is this point here on the other line? Nope, it's just on this line. Is this point here that I'm pointing to right here, is that point on the other line here? Nope, it's just on that line. But do you see a point that's on both lines? So if you said this one, you're correct. So in terms of graphing, the solution of the system in terms of graphing the solution of the system is the point or points where the two lines intersect. Right, so in terms of graphing, the solution of the system is the points or points where the two lines intersect. So if you look at this right here, if you look at this right here, the solution of the system is, and then what's that, 2, 5? Is 2, 5. The solution to the system is 2, 5. Okay? Now, you can always check. So, for this particular system we're talking about, and the system was this. It was y equals 2x plus 1, and then y equals negative 3 halves x plus 8. So my question is this: Is 2, 5 a solution? So is the point, the ordered pair 2, 5, a solution? Okay, that's the question. So to determine if it's a solution, remember this is your x, this is your y. So this is an ordered pair. So there's your x, there's your y. So in where we see the variable x, you would plug in 2, and where we see the variable y, you'd plug in 5. Okay? So you go back to the system, and in place of y and in place of x, in place of y and in place of x, you plug in these values. Alright, but you got to do it to both equations. And remember, it's got to be a solution to both equations. So it has to be 2, 5 has to be a solution to both equations. Both equations, in order for it to be a solution to the system. Okay, now, alright, so we go back to the original. So y is 5, so I'm asking myself, is 5 equal to, that's a question, is 5 equal to 2 times x, x is 2, plus 1? And you can look at this, 2 times 2 is 4, 4 plus 1 is 5, and the answer is yes. Alright, but remember, you got to look at the other one also. Alright, so let's go to the next one. Y is 5, so is 5 equal to negative 3 halves times 2 plus 8? So is 5 equal to this? Well, you need to do some work, so you're going to say 2 to 2 is 1, 2 to 2 is 1, and that is right here, that is negative 3 plus 8, which equals 5. So the answer is yes. So, therefore, 2, 5 is a solution to the system. Okay? Now, question's this. Is 6, negative 1 a solution to the system? Okay, so is 6, negative 1 a solution to the system? Well, graphically, so if you look at the graph, here's 6, negative 1. So is it a solution to the system? The answer is no. Now you got to be careful. You may say, well, it's a solution to this equation. That is true, but it's got to be a solution to this equation. So is 6, negative 1 anywhere on this line here? And the answer is no. 6, negative 1 is only on here. Okay? So if you look at the equation, you'll notice that 6, negative 1 is a solution to y equals negative 3 halves x plus 8 only, not a solution to y equals 2x plus 1. Alright, so therefore it's not a solution to the system. Okay, so now from all this, the takeaway you got to get is that when solving a system graphically, the solution is the point where the two graphs intersect. So the solution is the point that satisfies both equations at the same time. So when you graph lines, you're graphing solutions. So these points here are solutions to this equation, y equals 2x plus 1. So there's an infinite number of solutions to this particular equation. The solutions here, there's an infinite number of solutions to this equation. But in terms of the system, there is only one solution, and it's this. This is the only solution. 2, 5 is the only solution to this system here, to this system, because it's the only point that's on both lines at the same time. Okay? Alright, now, let's look at this. Suppose, alright, so given the system, and let's say my system's this. Let's say it's 3x minus 2y equal 4, and 2x minus y equal 1. So let's say that's my system. Alright, now the question is this. Let's see, is 3, 5 a solution to the system? Okay, part A. So is 3, 5 a solution to the system? Alright, so remember, it's a solution to the system. This is a solution to the system if it satisfies both equations at the same time. Alright, so if you go to the bottom equation, so let's check the bottom. So 2x minus y equal 1. So if you check the bottom one, you get, remember, this is your x, this is your y, so the ordered pair. You get 2 times 3 minus 5, and the question is that equal to 1? Well, 2 times 3 is 6. 6 minus 5 is equal to 1. So yes. So 3, 5 is a solution to this equation here. But that does not mean it's a solution to the system, because it's got to satisfy both of those. It's got to be a solution to both equations. So let's check the other one. So let's check 3x minus 2y equal 4. So in place of x, I'm going to plug in 3. And in place of y, I'm going to plug in 5. And the question is that going to equal a 4? Well, 3 times 3 is 9. 2 times 5 is 10. So negative 2 times 5 is negative 10. And the question is that equal to 4? And the answer is no, because negative 4 does not equal, negative 1 does not equal 4. So 3, 5 is not a solution to this equation. The ordered pair 3, 5 is not a solution to 3x minus 2y equal 4. So therefore, the ordered pair 3, 5, or the point 3, 5, is not a solution to the system. It's not a solution to this system. 3x minus 2y equal 4. 2x minus y equal 1. Okay? Alright, now part B. Is negative 1, negative 3 a solution to the system? Okay, so that's the question. So we do the same thing. Where we see the variable x, you plug in negative 1, and where we see the variable y, the variable y, you plug in negative 3. So let's check it. Make sure I'm doing okay. So yes, so we're going to go to the first one. So let's check the first one. 3x minus 2y equal 4. And in place of x, I'm going to plug in negative 1. In place of y, I'm going to plug in negative 3. So I get 3 times negative 1 minus 2 times negative 3. And the question is that equal to a 4? Well, 3 times negative 1 is a negative 3. A negative 2 times a negative 3 is a positive 6. And is that equal to a 4? Well, negative 3 plus 3 is a positive 3. So 3 does not equal 4. So the answer is no. So right away, since it didn't satisfy it, right away you can say that is not a solution. So negative 1, negative 3 will not be a solution. Okay, so all right, so let's look at this one. Let's suppose we had, all right, let's look at this system. Given this system, let's say this is a system, 2x minus 3y equal negative 4, 2x plus y equal positive 4. So is 1, 2 a solution? That's the question. So is 1, 2 a solution? Again, all you do is go back wherever you see the variable x, you plug in 1, and wherever you see the variable y, you plug in 2. So in place of x, let's go to the first one. So let's check the first one. So 2 times 1 minus 3 times 2. And the question is that equal to negative 4? Well, 2 times 1 is 2, and 3 times 2 is 6, so 2 minus 6. And is that equal to negative 4? And the answer is yes. All right. Now, remember a while ago when we did this one, when I did that first equation, and it turned out it wasn't a solution, don't waste your time doing the other one. Because if it's not a solution to the first one, it doesn't matter if it's a solution to the second one at all. It's not a solution to the system. So negative 1, negative 3 will not be a solution. Will not be a solution to the system. Okay. So here now, when I check the first one, it is a solution. But again, I can't say it's a solution to the system. I got to check the other equation. So I got to verify that this point is a solution to both equations. Okay, so let's check the other one. Let's check 2x plus y equal 4. So in place of x, I plug in 1. And in place of y, I plug in 2. So I get 2 times 1 plus 2. And I want to see if that's going to equal 4. Well, 2 times 1 is 2. 2 plus 2 is equal to a 4. So since the ordered pair 1, 2 satisfies both equations, then it's a solution to the system. Since 1, 2 is a solution to both equations, that means it is a solution. I'm going to say it, I mean the ordered pair 1, 2. So it is a solution to the system. Okay? Alright, so now the takeaway so far from this part is that you need to understand that when, in our case here, you'll be looking at a system of 2 linear equations. So when you have a system of 2 linear equations, you want to find the solution to the system. For the most part, you have to find the solution. And the solution's got to satisfy both equations at the same time. Now remember, when you look at each individually, there's an infinite number of solutions here. There's an infinite number of solutions here. But when we looked at the solution to the system, we saw there was only one of them, because those two graphs intersected at only one point. Okay? Alright, now, let's see if I need to discuss anything else. Okay, so one thing I need to mention, and let's do it now. So when you solve a system, and notice that this system here, had only one solution. There was only one solution, and those two graphs intersected at one point. All right. So when you look at the system of two linear equations, a couple of things can happen. The graph can the graphs can intersect at exactly one point. The graphs can end up being parallel, in which case they don't intersect. And it turns out that the graphs can also overlap. So this line, this equation, and the other equation can be the same line. All right, so those two lines intersect. And so notice that in this system here, there was only one solution. Okay, the lines intersected at one point. For the most part, what you're going to be dealing with will be this situation here, where you only have one solution. If you have a system where the two lines are parallel, they don't intersect, so that means there is no solution. So there won't be any solution. So the lines do not intersect. There's no solution. If the system, if the two equations, when you graph them and they overlap, meaning they're the same equation, the lines overlap. Notice that means, remember, they intersect here once, they don't intersect here at all, so no solution. Here, they intersect everywhere on those two lines. They intersect everywhere on those two lines. So there's an infinite number of solutions. So here, there's an infinite number of solutions. All right, and solutions are the points where the two lines intersect. So one intersection here, so one solution. No intersection here, so no solution. An infinite number of points here because they intersect everywhere in that line. Okay, now, if there's one solution, if you have exactly one solution, remember we're talking about lines. If you have exactly one solution, then that system is called a consistent system of equations. So it's called a consistent system. C-O-N S-I-S-T-E-N-T, consistent system. Okay? If the system has no solution, it's called inconsistent. Inconsistent. So that's an inconsistent system. So consistent, inconsistent. If the lines overlap, meaning they have an infinite number of solutions, that's called a dependent system. Dependent system. All right, so a dependent system. So one solution, consistent system. No solution, an inconsistent system. An infinite number of solutions, a dependent system. So the two lines intersect at the same places. Okay? All right, now that should be the end of this part of the end of part one. So solving a system of equations, linear equations, and just basic concepts. Okay, so let's. The next thing we're going to do is we're going to talk about solving a system using substitution. So we're going to stop here for this part.